Okay, in all the exam guidelines for work, energy and power, they strongly advise you to always draw these diagrams. So these are obviously, these force diagrams look a lot like the force diagrams in Newton's laws, because a force diagram is a force diagram, and if we're calculating the net force to calculate the net work, it makes sense to always draw the diagram. So if you look here at a block on a horizontal surface, there's a horizontal force F being applied to push the block that way. There's some friction going that way. There's the weight, and there's the normal force. These are the forces acting on the object. So if an object is moving on a horizontal surface, only the forces with a parallel component that are applied parallel to the plane and the friction are going to contribute to the net work. Okay, so this object, remember, it's got to do, work has to do with displacement in the direction of the force. So this object is going to displace that way in the direction of the force, okay, and then only this force and the friction are going to be there, important. This normal force and the gravity are at 90 degrees, and the cos of 90 is 0. So the work done by this force will be positive because the box is moving that way, and the angle between this applied force and the direction of motion is 0, and the cos of 0 is 1. However, if you look at this friction here, the box is moving that way, friction's going the other way, the angle is 180, the cos of 180 is negative 1, so the work done by this force will be negative. Okay, same thing here. If we look at this force, this rope is pulling this box this way, and there's friction that way. Only the forces that have got a component parallel to the plane are considered. So the normal and the gravity are not considered because they're at 90 degrees. So this box is moving that way. Only the x component is going to do work here. So it'll be the x component multiplied by the displacement, and this friction here is going to have it's all in the direction of motion, but motion is that way and friction is the other way, so it's got a 180 degree angle between the way the box is moving and where friction is acting, so this work becomes negative. So, and this is just reiterating here that the normal force and the weight are at 90 degrees, they're perpendicular to the plane, they are not going to do any work when the box moves. So this box moves that way, this box moves that way, the normal force does nothing, the weight does nothing, they are not doing any work, only this force and this force are doing work, the same with this box. So now let's look at when you pick up objects, okay, in the vertical plane. We obviously have to oppose gravity to lift anything up. So the moment you lift an object, the applied force has to equal the weight of the object, but in the opposite direction. Think about it, if you try and pick up something heavy, it's got a lot of weight, you need a big force. If you pick up something light, you need a little force, okay? So the applied force must be at least equal to the weight of the object, and if you want it to accelerate, the force must be greater. So when we look at this, this is now our link between work and energy as well. Work is measured in joules, energy is measured in joules, they are like comparable. So the work done against gravity equals the gravitational potential energy obtained by the object. So your EP, potential energy, is the mass of the object times the acceleration due to gravity, so this is the weight, times how high you moved it. So if you think of this in terms of an object being lifted upwards, if the bottom of the screen here is 0 and you lift it up to the bottom of the writing here, okay, you will have lifted it through this height h, but this height h is equivalent to delta x in the work formula. So we took the weight of the object, Fg, and we displaced it, delta x, so this would be Fg delta x, okay, but here it's exactly the same thing because Fg is mg and h is equivalent to delta x. So these two formulas are comparable, they just thought about in slightly different terms. However, you have to start thinking about net forces again when we have constant velocity. Remember, there's only a net force if you have acceleration according to Newton's second law. So if you just raise the object at a constant velocity, there's no net force. So the work done raising an object at constant velocity will be 0. Yes, physics, it's awesome. If you're on an inclined plane, the two perpendicular components don't contribute. So the normal force and Fg perpendicular don't contribute. Only Fg parallel is going to contribute because the objects can only displace on the plane here, and so work is only done in the direction of motion. Okay, so Fg parallel contributes. So if you look at all the parallel forces and you find the net force by adding them all together, that will determine the net work. Or like I said earlier, your second option is to work out the work for every single force and then add them together. But the net force is way better. Okay.